So hello guys, in the last video we have seen about sensible heating and cooling. So now towards the next topic, it's humidification and dehumidification. Today we will see about it. So now uh, the addition of moisture of the air without changing its density is known as humidification, and similarly removal of moisture from the air without changing its density is known as dehumidification. So we can see in the diagram, humidification and dehumidification both processes are given. In the humidification, basically specific humidity is increasing from W1 to W2, and in the dehumidification, specific humidity is going from W1 to W2. Basically, here we can see process 1 and 2 both having same temperature, which is dBT. Dry bulb temperature is constant here in this process. In this process, we can define also defined by latent heat. So this is the basic difference between the heating and cooling and humidification and dehumidification. In the humidification and dehumidification, there dry bulb temperature is constant and only moisture is adding to the air. In humidification, change in the enthalpy is shown by the intercept H2 minus H1 on a chart. Here in the chart, we can see point 1 and point 2. If we draw the line to enthalpy curve, so we will get H1 and H2. So difference between them is will be given by change in enthalpy. That is our humidification. Since dBT remains constant, therefore sensible heat also remains constant. So here total heat will be some. We know that the total heat is latent heat plus sensible heat, but here sensible heat is zero. So our total heat would be latent heat as we discussed. Now moving towards the content, thus the change in the enthalpy per kg of dry air is due to increase in moisture content equal to W2 minus W1 kg per kg of dry air is considered to cause a latent heat transfer. So now mathematically, latent heat is equal to H2 minus H1 enthalpy difference. So HFG W2 minus W1 also denoted by HFG W1 minus W. Here HFG is the latent heat of vaporization at the dB, because your temperature is constant at the TD1. Now we have discussed about these two processes, humidification, dehumidification, and our previous lecture we have discussed about the sensible heat and sensible cooling. So now mixing all these two properties, we will get these properties. Now basic properties I have discussed, and now moving towards the next topic, which is cooling and dehumidification. Where cooling and dehumidification both processes occurs simultaneously or step by step, means it depend upon our application, our machines, how we use to it. We can firstly do cooling and then humidification, or humidification then cooling. Both processes can be result same result. Now cooling and dehumidification. Here first process is, we can see here, first dehumidification is done and then cooling is done. So in result we get from point 1 to 2 is cooling and dehumidification. And in the second diagram we can say, first the cooling is done, sensible cooling is done, and then till the saturation line, and then on the saturation line its humidity is reduced, and this is dehumidification. The result from 1 to 2 we get as cooling and dehumidification. Now, this process is generally used in summer air conditioning to cool and dehumidify the air. So, the dehumidification of air is only possible when the effective surface temperature of the cooling coil, which is TD4, is less than the dew point temperature of the air entering the coil, TD1. So what if these two temperature are equal? So this would give us zero result, or we cannot see any result. So therefore this condition is mentioned here that temperature should be less than the TD1, means entering temperature should be more than the coil temperature. Now the effective surface temperature of the cooling coil is known as apparatus dew point temperature, briefly written as ADP. So now let's TD1 is equal to TD3 as discussed in the condition. DPT is of entering coil. So TD4 would be ADP here. Under the ideal condition, TD4 is equal to ADP. TD4 here is apparatus dew point temperature, which is coil surface temperature. It's never possible due to inefficiency of the cooling coil. We have in the previous lecture we have seen about the bypass factor, that there should be there is in practical condition there is always bypass factor is there, which is inefficiency of the coil, that cannot convert, say cannot give the same temperature as the coil. Therefore, resulting condition of the air coming out of the coil is shown by point 2. In the below diagram, we can see there we are getting 4 points, 1, 2, 3 and 4. In the ideal condition, point 2 and point 4 would be same, but due to bypass factor, point 4 and point 2 will be different. Here point number 4 define the bypass factor, or sorry, bypass factor not. Point number 4 and 2 line, it is bypass factor, difference between H2 and H4. And point number 4 is ADP of a coil. Point number 2 is outlet condition. Point number 1 is inlet condition. So now bypass factor we can see here, TD2 minus TD4 upon TD1 minus TD4, and also we can denote bypass factor with the help of specific humidity and enthalpy change. So this is written as W2 minus W4 upon W1 minus W4, and same as H4 minus H2 upon H1 minus H2. Now in this slide we will see about sensible heat factor. What is sensible heat factor? So sensible heat factor is the factor of sensible heat divided by total heat. It's actually ratio of total sensible heat upon total heat. Total heat in means total heat is a combination of sensible heat and latent heat. Now total heat removed from the air during this process is H1 minus H2, which is latent heat plus sensible heat, where latent heat is difference between H1 minus H2. In the right diagram, we can see point number 1 to 2 is our process, which is cooling and dehumidification. If we draw horizontal and vertical line, we get one point A, because we are getting this point to ease to calculate sensible heat and latent heat separately. If we draw the straight line to enthalpy, so we will get H1, HA and H2. So difference between H1 and HA we will get as latent heat, and difference between HA and H2 we will get as sensible heat. So in this way we can calculate sensible heat factor easily. So now sensible heat factor is sensible heat upon total heat. Sensible heat is HA minus H2, and total heat and latent heat is H1 minus HA. So putting this value in the formula, we get as HA minus H2 upon H1 minus H2 as sensible heat factor. Now line 1 to 4, we can see in the diagram, line number 1 to 4 is known as sensible heat factor line. Here this line is point number 1 to 4 is sensible heat factor line. Point number 1 to A is latent heat, A to 2 is sensible heat, point number 2 to 4 we have as bypass factor, and completely from 1 to 4 is sensible heat factor line. Now this is our psychrometric chart, with the help of which we solve the basic numericals. This is very useful chart, and it is taken from ASHRAE. Here we can see the sensible heat factor line, and we have to take the point, and then by the scrolling we can draw it sensible heat factor line here on the chart. And it is asymmetric chart. Here we don't have to draw the point and other things, because at the right side we have sensible heat directly given. So now we will solve a numerical based on the processes. Uh, in a cooling application, moist air enters a refrigeration coil at the rate of 100 kg of dry air per minute at 35 degrees Celsius and 50% relative humidity. This is condition of given to us for inlet air. Now, the apparatus dew point temperature of coil is 5 degrees Celsius and the bypass factor is 0.15. We have to determine the outlet state of moist air and cooling capacity of a coil in turn of refrigeration. Now, what we have, mass of air, which is 100 kg per minute, temperature, inlet temperature is inlet condition we have T1, and phi 1 is 50% relative humidity. Temperature of air is 35 degrees Celsius, and ADP as 5 degrees Celsius, and bypass factor as we are having 0.15. So how to solve it? Firstly, mark all the points on the chart. Here in the numerical we have inlet condition, so we have to draw here point number 1. Its dpt we can see 35 degrees Celsius and 50% relative humidity. Here this curved line are relative humidity line, so we can get here 1 point. Here we will draw our point number 1, and our ADP, we have our ADP. So directly coming to the saturation line at the 5 degrees Celsius, we can draw point number 3, which is our ADP. Now we have to get our point number 1 from the bypass factor. We can directly say that the point number 2 we will have between point number 1 and 3 as property of bypass factor or inefficiency of a coil. So now checking dpt of entering air, ADP of coil should be less than the dpt. This is main condition of cooling and dehumidification. Now using the bypass factor, we have bypass factor and point number 1. So after with the help of enthalpies and this temperature, we can easily get the point number 2, or we can say temperature of point number 2. So putting the values in bypass factor is TD2 minus TD4 upon TD1 minus TD4. In the numerical we have taken TD4 as a ADP or point or surface temperature of a coil. Now TD2 we don't have, TD1 we have as 35 degrees Celsius. 0.15 is equals to TD2 minus 5 upon 35 minus 5. So we get TD2 as 9.5 degrees Celsius. So here in the chart we will draw 9.5 degrees Celsius on that line. Point number 1 to 2, sorry, point number 4 to 2, 4 to 1 line we are having. Now we have to intersect just 9.5 degrees Celsius on that line. So we will get that point. And with the help of that point, here in the diagram we can see here point number 2 we will get. Now taking the enthalpy at point number 2, and we are having enthalpy at point number 1, so we can calculate its refrigeration capacity of a coil. Refrigeration capacity is basically enthalpy difference of point number 1 and 2, means what change of enthalpy is done by the coil. So that basically we have to calculate enthalpy between H1 and H2. We have taken H1 minus H2 multiplied by mass flow rate, so we will get 5300 kilojoule per minute. Now we have to calculate into turn of refrigeration. So 200 we have to divide by 210 to get in turn of refrigeration. If we are having value in kilojoule per minute, then we have to divide by 210, and if value we are having kilojoule per second, then we have to divide by 3.518. So we will get the value into turn of refrigeration. So our final answer is 25.25. to 4 turn of refrigeration. Means this much amount of energy would be required by cooling coil to change the temperature from 35 degrees Celsius to 9.5 degrees Celsius. So that's all for today.